Okay, so in this discussion section, I would like to go through the topics like Laplace transformation, right? Like show you how it works and how to solve problems. So feel free to unmute yourself and ask questions. So whenever we have a function ft, we can always like do a transformation. Let's denote fp from 0 to infinity and ft exponential minus pt dt. So this is called the Laplace transformation. Original function is a function of t, and after the transformation, the function is like the argument is p, right? So one thing I want to point out is we really don't care about this ft from negative infinity to 0. We only care about ft from 0 to infinity, right? You can say from this integral range is from 0 to infinity, so we don't care about what it looks like. Yeah. Okay, so we can we usually use this Laplace transformation to solve differential equations.
I had a quick question.
Sure.
Are there any restrictions on the types of functions we can transform with this?
I don't think so, because like I mean the only constraint I think is to make sure this guy is converge. You can get a right, but you can say there's a exponential factor here, which make many diverged function become converge actually. So
Okay,
yeah,
right.
yeah, that's was a nice thing. The reason why we put an exponential here. Yeah. Okay, so to use this transformation to solve differential equations, this is one usage of this kind of transformation. Solve differential equations. So to do that, you need to know. Okay, so let's introduce some notations. Y prime usually is just a derivative of a function yt, and the y double prime is just a second derivative of this guy. And we can do a Laplace transformation for the first derivative of this function y. This will give us, I'm pretty sure the professor showed in class, and this is p times y, the Laplace transformation of function y, and minus y naught. Y naught is the initial condition, should be given in the problem. And also the Laplace transformation of this double prime is given by p squared y and minus p y naught and minus y naught prime. Y naught prime is also the initial condition, should be given in the problem if it's a second derivative equation, differential equation, which is nothing but this, right? So once you know these two equations, and yeah, you can use it to solve the differential equation. So let's say an example. Okay, so I have a z prime plus 2y equal to 0, and also y prime minus 2z equal to 2. It's a couple differential equations. And the initial condition is y naught equal to z naught equal to 0. Okay, so whenever you have this kind of coupled differential equations, and also the initial condition is given, it always easy. if we use the Laplace transformation, the basic idea of this Laplace transformation is transform this kind of a differential equation to algebra equation and solve this algebra equation in using the the standard algebra, linear algebra. You will get like a YD as a function of P equal to something, and the Laplace transform YP, and then not Fourier transform. It's a Laplace transform back to your original space, right? So instead of solving a differential equation, we solve an algebra equation. That's much easier, and yeah. So that's the basic idea. And to do that, let me show you the algebra. Feel free to stop me if you get confused. So let's look at the first equation. Basically, we need to transform the whole equation, which is z prime plus 2y equal to the second equation. So never forget to transform the right-hand side. From my experience, like students usually just forget to transform the right-hand side. Sometimes it's 0, sometimes it's a constant. So it's easy to forget. So yeah, otherwise, if you forget, you will get a wrong result. And so yeah, just remember. So the Laplace transformation of this guy is, z prime plus 2ly equal to the Laplace transformation of 0 is 0, right? If you set this ft to be 0, then it's 0. Right? And this guy is the Laplace transformation of z minus p times this guy minus the z naught, right? So this guy is itself. And we also Laplace transform the second equation. So I'm showing the steps in detail. So the Laplace transformation of this guy, 2, which should be 2 over p, right? And okay, so this guy is also PLy minus 1 naught. So remember the initial condition tells us y naught, z naught, and y naught are both 0. So we get a differential, we get an equation like this. We'll get 2 equations. So this term plus this term equal to 0. And this term minus this term equal to 2 over p. So if you forgot to transform this right hand side, you would get 2 instead of 2 over p. So you can say we kind of translate this kind of a differential equation into an algebra equation. There's no differential operation in these 2 equations, and we can solve it, right? To solve it, there are many different ways. I guess you have your own familiar way to solve this kind of differential equations. Algebra equations. For me, the easiest way to solve this is by writing it in matrix form. You don't need to follow my method. So this is p, this is 2, this is minus 2, this is p. right? And v1 equal to p2 minus pp inverse 32p, which is something like p squared plus 4 and pp minus 2 2 0 2 pi. It's not 2 over p, which is eventually you get the LZ is what? LZ is minus 4 pp squared plus 4, and the Ly is 2 over p squared plus 4. Right. So yeah, any question about what I said here? Okay, so if you have no question, let's continue. So basically we have the LZ equal to this guy minus 4p squared plus 4, and the Ly is 2p squared plus 4. And of course, sometimes like people call this guy, or use a new notation from this guy is the capital Y. P, this guy, I don't know, maybe capital Z, P. It doesn't matter, right? It's just notation. And we know that the original function is the inverse transformation of this guy, which is the inverse transformation of this guy. And you just need to look at the table, look up the table, and you would say it's it's like a minus. There's a minus sign. 1 minus cosine 2t, I think, is cosine 2t minus 1. So this is zt. Similarly, for the yt is also the, you just need to transform back to the time domain, which is the, you just look up the table. It's like a sine 2t. So the solution for this problem is sine 2t, zt equal to cosine 2t. So any question for this problem? Okay, so I guess it's clear. So one thing I want to point out is whenever you solve this kind of differential equations, it will always useful, like a very convenient to check whether this is true by plugging to your original differential equation when your solution is quite simple, right? At least you can check the initial condition. So the initial condition tells us when t equal to 0, both y and z vanish, right? So you just need to set t equal to 0 to see whether your solution match with the condition given in the problem. So t equals 0, sine 0 is 0, indeed is 0. And cosine 0 minus 1, cosine 0 minus 1 is 1 minus 1 is equal to 0. So you can say at least it matched the with the initial condition in the problem. And because the solution here is quite simple, sine cosine function, we can do the derivative quite easily, and let's check whether it's true or not. Copy. Okay. So z prime. So what is z? Oops. What is z prime? Z prime, according to our solution, is minus 2 sine 2t, right? And the y is sine 2t. So z prime plus 2 times y. Indeed, it's 0. And you can also check this y by yourself, this second equation by yourself. And yeah. So in addition to show you the algebra, the basic process to solve this kind of differential equations using the Laplace transformation, what I want to say is there are 2 points. One is don't forget to transform the right-hand side. And this, I mean, because I taught this class like last year, I found many students just forgot to transform the right-hand side and get a wrong result. Just, yeah, just be careful. And another thing is whenever you get a result, you can check your result. You can check your result, for example, by plugging the initial condition and see whether whether it match with the initial condition given the problem or not. If your solution is quite simple, like what we have here, you can even plug in to your differential equation to see whether this is true. Okay. Some very useful useful stuff. It's always good to check your solution after you solve the problem. Okay, if you have no question, let's continue. Another topic is about the convolution, right? So basically, it's like I have you know imagine. Okay, so let's look at this. If I have 2 functions in time domain in the original space, and after the Laplace transformation, and you get a capital GP, basically it's LG, right? And HP. What if I have a function like this in, oops, let's write. What if I have a function which is the multiplication of those 2 functions? Like ask you what's the corresponding function in the time domain. So basically we need to calculate the inverse of this guy, right? And the convolution theorem or whatever, you can prove it by yourself. It was in the textbook. This guy is given by the acting on this, the first one, convolute with the L inverse acting on the second one. We know that this guy is nothing but small g. Convolute with this guy is nothing but this guy. So it's HT. And the definition of the convolution is from integration from 0 to t and the g t minus tau and h tau d tau, right? Of course, you can change the position h t minus tau g tau d tau. Doesn't matter because you can see there's a symmetry in your expression here. Of course, g times h equal to h times g. So you can also exchange the position for the g and h here. So basically, the convolution tells us how to calculate the inverse transformation of this kind of a product-like object. Any question about this part?
Hey G, I just want to know like when to use convolution versus when to like look things up from the table, because sometimes you could like put the in transformations together from the table. You don't have to do the convolution.
That's true. Okay, so I'll show you an example. Okay, so example y prime plus omega square. Oops. Ft and the ft is nothing but 1 0 so t to a and otherwise, and the initial condition is, and the question asks you what is yt. So whenever you have this kind of problems, like when you have some ft on the right hand side and the ft looks kind of complicated. For example, in this case, is a piecewise function. In this case, I'm pretty sure there's no, you cannot. There's no corresponding like how to say. There's a no corresponding like a Laplace transformation in the table you can look up. In this case, you can use this kind of a convolution, and of course, you're right. For example, even for this kind of a simple, p plus a square, like 1 over this guy. Of course, there. If you look up the table, there should be something tells you what is this. I don't know. I didn't remember. And of course, you can also apply this kind of convolution to solve this problem, right? This guy equal to what? Equal to the inverse of p plus a, 1 over p plus a. This is what? Apply the convolution theorem. And you can look up what is this. Let's denote as gt in the table. I'm pretty sure there is a one. And this is also gt, right? So it's basically is g star g, which is from 0 to t, and gt minus tau d tau. So you can say when you have some functions that is complicated, you can apply the convolution. And when your function is simple, you can also apply the convolution. So it's just a method to help you to find the inverse transformation. So whenever you cannot find something you want in the table, you can try to apply this convolution. And yeah. Okay.
Thank you.
Sure. Okay, so let's look at this problem. I think there is a similar problem in your homework. Like on the right hand side is a kind of step function, or not step. It's like a piecewise function. So first, we can draw this function. It's always useful to draw this like a function and using a graph, like to get some intuition. So it's a function defined from 0 to infinity. We really don't care about what's happening like in this kind of a negative regime. So from 0 to a is 1, and from otherwise is 0. So we can say there's some discontinuity at point A, and we can expect that the function y should somehow also a piecewise function, and like when t smaller than a is something and t larger than a is something, right? This is our intuition. I mean, it's quite intuitive, like because your force is kind of a discontinuous. Of course, your response somehow should reflect this discontinuity in your force. Okay, so this is some basic analysis we did, and we have some intuition. Let's go and let's solve this differential equation using the Laplace transformation. So, Laplace transformation to just apply to this guy, which is this. And okay, so I just write all the steps for you. Oops, there should be omega square equal to. So never forget to transform the right-hand side. I mean, you don't have to write all the steps. Like if you are familiar with this kind of stuff, you can just write down this guy directly. So you can say from this step to the third step, I use that the Laplace transformation is a linear transformation, right? Meaning that you can apply to the first one and also to the second one. Okay, so okay, what's this? This is p squared Ly, right? Because the initial condition is y not is 0 and y not prime is worth 0. So this guy is p squared and times y plus omega squared y equal to yeah. So we get Ly is p squared plus omega squared. We get this condition. So any question up to this step? Okay, so so then we need to, inverse transform this y, right? Y equal to, according to definition, the inverse transform of this guy, which is just plug in, right? This guy equal to this guy, so it's y. What's this? So in this case, your LFT, of course, you can do the Laplace transformation to find what is this guy, but it's quite complicated. In this case, we can regard this guy is a product, right? Of course. And this is inverse of, now I apply the convolution theorem, which is this guy convolutes with this guy. So what's this guy? So you can look up on the table. I really didn't remember what it is. I think it's omega sine omega t. Convolute with this guy. This is nothing but the ft, right? Because L inverse L, meaning nothing, meaning so L inverse cancel with this L, so left with F, which is, so, it's from 0 to t, and sine omega t minus tau omega f tau d tau. So this is our y. Is it clear what I'm doing here? Or any questions, just let me know.
The reason you're picking sine is because f is unknown. Is that right?
Yeah.
Okay.
So here I didn't calculate this guy because I know that eventually I need to transform it back to the original space. So I just keep it ft. But we know what is ft. Ft is like a piecewise function like here. So we know this sine we know this guy, we know this guy, we can do this integral in principle. And it's also tricky, like to do this integral. So I want to show you how to do it, like in detail, so that you can avoid making any mistakes during the exam. So I know, even though I I talk about this in discussion, students will always also make mistakes, but I will try my best. So FT is something like A and something like this, right? This is your t-axis. Now imagine, so because your y is a function of t and t is some positive value, like a number, right? So if t is in this regime, t is somewhere here, then your f tau is always 1, right? However, if your t is larger than a, is here, then when you need to split your integration into 2 parts. It's from 0 to a and from a to t, right? If your t is larger than a. So from 0 to a, your f tau is 1. But from a to t, your f tau is 0. Meaning that we need to consider 2 cases. Basically, when t is smaller than a, in this case, so this is our first case. Your yt is given by from 0 to t and sine omega t minus tau divided by omega and f tau d tau. So in this case, your f tau is 1 because your t is here. So we really care about the regime integration over from 0 to t, like here. In this regime, your ft is 1. So it's from 0 to t and omega sine omega t minus tau d tau. And then just do the integral. What's this? It's from this omega square. Remember, we're integrating over tau instead of t. Sometimes you may make mistake. This is cosine omega t minus tau, t from 0, which is omega square. The numerator is given by, so t, when tau equal to t is 0, right? So it's cosine omega t minus tau equal to t minus cosine omega t minus 0, which is omega square 1 minus cosine omega t. So any question about this case?
Is tau just a dummy variable?
Sorry, can you say it again?
Is tau just a dummy variable?
Right.
Okay.
Yeah, tau is a variable we need to integrate over, right?
Right. So it's not a transformed new space, it's just a different dummy variable.
Yeah, it's just a dummy.
Thank you.
Okay, so whenever you do this kind of integral, you always should be careful, like be clear, like what's the variable you're integrating over. So in this case, your tau is a variable you're integrating over, and t in this case you can regard it as a fixed variable, fixed number. So you need to consider 2 cases: when t is smaller than a, and another case is when t is larger than a. When t is larger than a, let's copy this guy. Copy. Oops. in this case, you need to split your integration range from into two parts. One is from 0 to a. Another part is from a to t. So from 0 to a, the f, you can say is from 0 to a, the f is 1. But from a to t is 0. So ft is 0. So when f2 is like this. And what's this? This is the do the integral, which is remember the variable is tau instead of t. So omega squared cosine omega t minus tau. Tau in this case is a, and minus cosine omega t minus tau. Tau in this case is 0. So omega squared cosine omega t minus a minus cosine omega t. Yeah, this is yt. So any question about this part?
What was the purpose of doing the previous section? I don't understand what the difference is.
Oh, so you mean here and here?
Yeah.
So here, so basically, so when your t is smaller than a, your f, remember your f, the argument is tau, right? Tau is always over this kind of integration range. You can say when your argument is from 0 to t and t is smaller than a, meaning that your f, this f function is always 1. However, if your t is larger than a, meaning that now I'm integrating from 0 to some value here, then your f tau is 1 in this regime, but from a to t in this regime is 0. So you need to consider consider them separately, and this is what I'm doing here. And basically, this is because your f tau ft like your function f is a piecewise function, and that's what I'm doing here. And of course, you can write this f, the y function, cosine omega t, omega square, and cosine omega t minus a minus cosine omega t, and t minus a, t minus a. This is the final solution. And as you can see, this actually matches with our original intuition, like what we said before we start. Because your force is a piecewise function, before time t, before time a, is a constant 1. After time a, the force just disappear and it's 0. The force is 0. So in it, this y can be regarded as a position. So your position as a function of time should also have some, discontinuity or something that can reflect the discontinuity in your force. You can see here, your position indeed, they have different expression at within different regime. By the way, you can also verify, like what we said before, we can also verify this initial condition. So when you can plug in t equal to 0, because when t equal to 0, So you should use this guy, t equals 0, like a cosine 0 is 1, so 1 minus 1 is 0. And you can also take a derivative. You would get something proportional to sine omega t, and plug in t equals 0, you also get 0. So corresponding to those two initial conditions. Any question about this problem?
A quick question, like when you said when you want to plug in like t equals 0, I think it's only it is only for the first case, right? Because like 0 is smaller than a.
Yeah. Sure. Yeah. I'm working on this guy.
Okay.
No.
Thank
By
you.
the way, yeah. Any other questions? Yeah, make sure you know how to solve this kind of problems. I guess I think there's a high possibility that this kind of problems will appear in the exam. Okay. So by the way,
I have a question. Could you scroll up to where you define the function f of t, I believe?
Sorry, can you say it again?
Yeah, right there. A little bit higher. Wherever you defined f of t.
Oh, f of ft?
The right side of the equation where it was like a piecewise function.
Right.
It was what was the values exactly? It was 1 on 0 to a and then 0 otherwise, right?
Right.
So there, even though f of t is 0 when t is greater than a, y isn't 0 when t is greater than a. The function y, it actually has a value when t is greater than a, even though f of t is 0.
Solution at the bottom with cosine of a.
Yeah. I guess it seems kind of unintuitive that even though f of t is greater as 0 when t is greater than a, y of t.
You mean we should somehow get 0 here?
Yeah.
Okay, so let's back to the physics. Okay. Let's look at what this equation describing. So basically it's y double prime plus omega square y is a very good question. Thanks for asking. I mean, as a physics student, you should always ask question like this. So basically there are two forces. One is a spring force. So imagine you have a spring connect with your like an object, whatever. And because the initial condition is like the velocity is 0 and also the initial position is 0. Initial velocity is 0, meaning that it's in the amplitude position, right? The initial velocity is 0, I think so. And okay, so okay. Maybe let's see in this way. Or I think you can also start from the initial equilibrium position, because there is a force. So the problem is like this. At time t, when time is from 0 to a, there's a force applying on this object from 0 to a. So it will start to move. In this case, there are two forces. One is the external force, Ft, and there's another spring force. So the motion of this object is the result of those two forces. Of course, there's some motions, but after time t, if you set this force to be 0, meaning that there's no external force, but there's still a spring force. So for example, at time t, you're at position somewhere here, then you said, okay, there's no external force, but there's still spring force. So it will start to oscillate. So the position should be non-zero.
That makes sense. Thank you.
Yeah, you can say that when you set t equal to a, so the position equal to 1 minus cosine omega a divided by omega squared. This position is non-zero, meaning that there's some potential energy here, and it will start to oscillate, and yeah. And also you can say this y is actually a continuous function, even though it's a piecewise function. So if you set t equal to a, you can say here is 1 minus cosine omega a divided by omega squared. So here, if you set t equal to a, you will get the same thing. This also makes sense, right? Because your position of your object will not change discontinuously. It's a continuous motion, right?
Yeah.
Okay.
Thank you.
Yeah, cool. Okay, so this is a very nice question. So what's the next thing I want to talk about? Okay, so it's a delta function. So I actually talk about Dirac delta function or not in previous discussions, but okay, so there's a type of questions you need to know how to solve. It's like it's also similar to your homework problem. Oops. Basically, you have some, let's see. You can always understand this kind of differential equation using the simple harmonic oscillator. So this guy tells you the frequency is the square root of 5, right? Meaning that there's some spring and which provide you a frequency square root of 5, and this guy tells you there's a friction because it's proportional to your velocity. So there's a friction, and this guy tells you at t equal to naught, at t equal to t naught, there's some delta function like force acting on your object, and ask you something about your position as a function of time, things like that. And to solve this problem, okay, so because I think we are running out of time, only one minute left, rigorously. So let's, okay, so anyway, I will upload my notes later on the CCLE, but I just want to show you like, yeah, basically, you also apply the Laplace transformation on both sides on the whole equation, and you would get p squared times y plus 4py plus 5y equal to exponential p t naught. And then, you get y. By the way, y is the Laplace transformation of the function y, the position we want to solve, which is exponential minus p t naught divided by p squared plus 4p plus 5. And then you need to calculate this guy. So why not? Y as the inverse of the whole thing here. And then we can also apply the, the convolution theorem. And this guy is it's nothing but exponential minus 2t sine t. You can look up on the table. Basically, you need to write this guy as complete square. Things like this. this two corresponding to this two here, this one corresponding to this one here. And this guy is a dead function. And then do the calculation. This is also a piecewise function. So basically, exponential minus 2t minus t naught and sine t minus t naught when t is larger than t naught, and is 0 when t is smaller than t naught. This make perfect sense physically, right? Because remember, our initial condition is y not equal to 0, y not prime equal to 0, meaning that the object is in equilibrium. Like the displacement is 0 and there's no velocity. Of course, when t is smaller than t naught, this depth function is 0, meaning that there's no driving force. So the object will stay there. So the displacement is 0. But after the time t naught, so right at the t naught, there is a depth function. So that force, like that function like force. So it will start to move. Then, but because there's there's a friction. There's a friction. So eventually it looks like an oscillation, but gradually like the magnitude will decay to 0. That's the reason why there is an exponential decay factor, and also there's a sign factor. This sign factor captures this kind of oscillation, but this decay factor captures this kind of friction force. Yeah. So that's all I want to say today, and yeah, cool. Any questions?
Yeah, if you have a minute, I'd love to just glance at that integration you did. I still don't understand why we did the piecewise twice.
Oh, sure. Yeah, that's important. Yeah. So, by the way, if you have no question, you're free to go. And if you have question, you can stay here and we can discuss.
Yeah, all this makes sense in doing the piecewise, but I don't understand why we did it twice. I'm a little confused about that.
Oh, so it's here, right? Like
Yeah.
Yeah. 1, 2. Okay. So that's okay. It's some messy here. Let's start. Yeah. So basically, we have a ft f function from 0 to a, and now, well, we want to do an integral sine omega t minus tau. Let's ignore this omega here. Oh, okay.
I think the only thing I'm confused about is why we did an integral from 0 to t and then another one from 0 to a.
Oh, okay. So it's always integration from 0 to t. The reason why the second one is an integration from 0 to a is because there's another. So we split this 0 to t into 0 to a and a to t. From a to t, the f function is 0. So this term goes away, and left with this from 0 to a.
Then why is that the case in the piecewise function of t greater than a?
Because when t greater than a, okay, so imagine imagine this t. Okay, maybe so your confusion is about t larger than a, right?
Yeah. So we end up integrating from 0 to a, but then that ends up being the piecewise function result for t greater than
a. First, you should understand the t here is from 0 to r. So because this guy is a function from 0 to infinity, right? and it's quite natural, I would say. You should consider two cases and how to say that? So t larger than a. So when your argument is here, I mean, maybe I change a variable is easier because t is a little bit confusing. Let's set it as a b. So integration from 0 to b. If your b is larger than a, then
f goes to 0.
It's from a to b. Sine omega b minus tau f tau d tau. And sine omega b minus tau f tau d tau. Pass from a to b sine omega b minus tau f tau d tau. And
the first one goes to 1, the second one goes to 0.
Right. That's what I'm saying. Yeah, this guy is 0, this is 1.
Yeah, that all makes sense. I just don't understand. We do that piecewise twice, and I don't understand why the bounds go 0 to t in the first case and 0 to a in the second case, and then why those count as t less than a but t greater than a as our cases. The teacher didn't explain this yet, so I think I just probably am confused about convolution.
Wait, can you say it again?
Yeah. So we did that whole process twice. We do the piecewise a and b cases twice, one for t less than a and one for t greater than a.
Right.
But each time we're integrating from before and after a, and I don't understand why we have.
I see. Okay, it's a matter of doing integral, right? So let's back to this. So basically, yes. The only integral you need to do is this integral.
Yep.
Nothing else. The problem is okay, let's say I have a person. Now let's say a equal to 10 seconds, okay? And now as like your friend asks you what's the position of this particle, of this object at like 5 seconds.
Yep.
Then what you need to do is to from 0 to 5 sine omega b minus tau f tau d tau. I agree.
Yep.
So okay, in this case, this guy is 1, right? Yep. Meaning that there is a driving force, and you get something non-trivial. Now, if there's another friend ask you, what's the position of this box or particle at 15 seconds?
Yep.
Now you also need to do this integral.
And that'll be 0 to 10 still, because the 10 to 15 goes to 0.
Exactly. You notice that, by the way, this integral is kind of accounting the effect of this driving force, right? You notice that this driving force only effective from 0 to 10, because beyond 10 seconds is 0, right? So it's given by sine this guy d tau. So you get a number.
Yep.
This is exactly what we are doing here.
Yep.
It's like a splitting into two cases.
I know now.
Yeah, I understand those cases, but yeah.
Brennan, I think you're asking is why the solution of this b greater than a is the solution portion for t greater than a, right? So G, can you scroll up a little bit?
Where? Sorry?
Scroll up to the solution of the.
Okay, sure. Where is it?
So if you go to right there, the solution part. So is it what you're confused about, Brandon? So the bottom part, cosine of omega t minus alpha part is, so the integral itself is integrated from 0 to a,
Yep.
but it is part of solution for t being greater than a. Is that what you're?
Yeah, I think I'm just confused about the fact that we do that piecewise twice, and we use t greater than a and t less than a for each of these piecewise cases in the result.
Yeah.
I buy the result and I buy that it is true. I'm just not convincing myself why.
I think it's solely because of like, I think you're looking, I'm not sure either. I think that, so when the t value is greater than a itself, right? The function, because this is, notice this is the position function instead of the force function.
Yep.
So what happens is that, so if you're integrating t less than a, then the function behave like on top. But if your t is any value greater than a, then the function itself in the bottom. But both functions are the same, because if you plug in a, they yields out the same function.
Right. Yeah.
I think that's the reason.
Yeah. I think.
You know what I mean? So I think you're trying to imagine this in geometric sensation, maybe.
Yeah. I'm just going to read the section and try to understand.
Yeah.
I have a confusion that I can't explain.
Yeah.
So, thank you, G. I appreciate all the time.
Yeah, I know what you mean, right? So like physically, like this t is like, it's a piecewise function, and then when you integrate it, the only part that counts is 0 to a. But in the solution part, it is representing this part of where t value is greater than a.
Actually, that makes sense to me. I don't think that's the part I'm confused about. So,
Now I'm confused on the other part.
we're all confused. Great. All right. Yeah. Anyways, well, G, I appreciate all the time, man. Thanks for all the
Yeah.
getting.
Yeah, it's good to get confused.
Yeah.
We need to learn more. Yeah.
All right.
Yeah. Any other questions?
No.
Okay.
Bye, G.
Bye.
I'll see you.
G, you have office hours from like 4 to 6 on Thursday, right?
Right.
Okay. Sounds good. Okay. Thank you, G. I'll see you then, and then on Friday on Thursday again for the review.
Yeah. See you.
Thank you.
Mhm.